Very good afternoon to one and all. I'm M. Ramesh, working as an assistant professor in the Department of Aerospace Engineering at SNS College of Technology, Coimbatore. In today's session, I'm going to explain about the Shear Force Diagram and the bending movement diagram in the overhanging beam. In the earlier class, we have discussed the cantilever beam over point loads acting on the beams. In this class, we are going to discuss the overhanging beam and how to draw the shear force diagram and the bending moment diagrams. See one by one. Here the problem is given to draw the shear force diagram and the bending moment diagram for the beam given below. Here we have to first identify the type of beam. Here at support A as well as at point B, roller support is there. At point A we have a hinge support. So two supports are there, but both are not at the end conditions. The first support at A is at the end, left end, and right end we are not having support. So the support is inside, not at the end. So this is called overhanging beam. And the type of beam is identified as a overhanging beam. Then what about the loads acting on the beam? So there are three loads are there. One is 20 kilonewton, 30 kilonewton, and 15 kilonewton. All are point loads, and they are acting towards downward direction. At C, D, and E, supports are being at point A as well as point B. What about the span of the beam? So total span is equal to 2 plus 3 plus 2 plus 2. So it is a 9 meter over the entire span, as well as the span distance for the each and every point is given 2 meter as well as 3 meter, 2 meter, 2 meters. The point load, that is the region AC, CD, DB, BE. The span is given. For this case, we have to find first the step is to find the support reactions. That means at point A we have a support reaction is there, as well as point B we have a support reaction. So these two to be found out. So the first step is calculation of support reaction. As per the diagram, we have a support at the point A as well as the point B. At point A, we have support reaction as RB, let's take, as well as RB here we can take. How to find the support reaction? For that we have to use statically equilibrium equation. Statically equilibrium equation. One is the summation of all horizontal forces. Here sigma fx, that means horizontal x-axis, all horizontal forces. If you add, everything will be equal to 0 with the sign convention. But here we have RA, RB as well as 20, 30, 15 kilonewton. All the loads are only vertical load, so there is no horizontal loads are there. So sigma fx is equal to 0. We cannot apply since there is no horizontal load. Then we can go for the vertical load. All sum of all vertical forces are equal to 0. Let's take the sign convention. So upward force, let's take as a positive. Downward forces are to be taken as the negative forces. So here RA plus RB and minus 20, minus 30, minus 15, that is equal to 0. That is the thing being given here. So RA plus RB, it is equal to 65 kilonewton. So as per the statically equilibrium equation along the vertical axis, we can have an equation like RA plus RB, that is equal to 65 kilonewton. But we have to find RA and RB separately. For that we need another equation that is called a statically equilibrium equation called bending moment. The sum of algebraic sum of bending moment at any arbitrary point we can take is 0. For that we are going to take at point A. At our point A here, so bending moment is to be calculated by the force into perpendicular distance. So we are going to take the bending moment at point A here. So all the forces 20, 30 and this RB as well as 15, all the loads to be traveled to point A. For that sign convention to be taken as clockwise as positive, anti-clockwise is negative. Only this RB will travel to A as anti-clockwise. Other loads are acting downward will travel to A in the clockwise manner. So this 20 into 2 plus 30 into the distance 5 RB into this 2 plus 3 plus 2. So this is negative, that is 7, and 15 into 9. So all these three loads will have a clockwise movement. Only RB will have a negative bending moment. So like that we are having here. So finally we are getting the equation that RB directly we are getting 46.42 kilonewton. Already we have found RA plus RB equal to 65. So RB equal to 46.42. So remaining RA value equal to 18.58. That has been placed here. 46.42 here, and RA will be equal to 18.58 kilonewton. Then let's move on to the shear force diagram. For that I need each and every point shear force values. So at from this side you can take at A point, C point, D, B and E. So what about the shear force? Shear force means you have to add the values, point loads directly with the sign convention. Left up is positive, right down is positive. Let's take left side. So towards upward side. So toward up, left up, that is positive. So RA equal to 18.58. Okay, this is, and here we will take a so RC. Here also there is no load. The RC value is, that means the shear force will at equal to 18.58 at CLU. What about at point D? You add these two. So 18.58 minus 20, that is the value, that is finally equal to minus 1.42 kilonewton. At point B, how to find the shear force values? So this value, this is positive, negative, negative, and this will be, so in between at point B you will not have that value, say minus 1.42 only. At B point we will have this 18.58 minus 20 minus 30, then this RB. So 46 point, this is positive, 46.42, including we are getting the 31.42, since it is negative value, minus 31.42 kilonewton. And if you add this 46.42, that will become as 15 kilonewton. And at the point E you can have here, okay, so the same value will come into picture, 46.42, that means 15 kilonewton here. And if you go this side, we don't have any load at the right side, otherwise it's equal to 0 only. Then how to draw the shear force diagram? First draw the zero shear force line or neutral shear force line as a linear line, a straight line. So upward is positive values are to be marked there, downward are being negative values. First place the values at A, here from here. But at A, what is the value? At B, at C, at D, at E. Okay, like that you can mark the values. Then here no load, so horizontal line will come. C to D also there is no load, D to B also there is no load, as well as B to E there is no load. Okay, only at the point we are having the loads. At that point we will have certain increment or decrement, that kind of way. So at point C it will decrease from 18.58 to minus 1.42. So 18.458 to minus 1.42, vertical decrement, you just show it here. And at point D minus 1.42 to minus 31.42, so you just have a decrement vertically. And at B point you will have minus 31.42 to 15, so minus 31.42 to 15, vertical increment. And finally here there is no load, finally it will become as 0. So this kind of way we can draw the shear force diagram. If UDL will come into picture, that will be a different diagram. But if there is no load, only point loads are there, in between no region, there is no load, you just draw a horizontal line. Then at the point of application you will draw a vertical line towards increment or decrement. That is the shear force diagram. So according to the values you just place at each and every point, get the values and draw the diagram, shear force diagram. Then we can move on to the step 3 is calculation of bending moment, that is force into perpendicular distance. and we already know that this is at point E and at point A, both are at the end condition. At the end condition we don't have any loads. That means at this point at E, force into perpendicular distance, so 15 into at E point, if you are taking, there is no perpendicular distance, that is equal to 0. As well as if you are taking A point, consider left side alone, so this RA into, also there is no perpendicular distance, 0 if you consider left or right. Next we can move on to the point C. So at point C we draw this reference line. So for that the bending moment, the sign convention is always the perpendicular, there is a vertical upward force will create the positive bending moment. So this RA, so yeah, I'm going to mark on the point at C. So RA will move on to point C. So it is in the clockwise. There is upward force will create the positive element. So 18.5 into 2, that is equal to 37.16 kilometer meter. So here at a bending moment at point C, at bending moment at point D. Bending moment point D, let's take same thing, is RA into 5 meter. Okay, then this is minus 20 into 3 meter. Okay, so that is equal to 32.9 kilometer meter. What about at point BMB? At point BMB, we can have right side also is 15 into 2, so at least 30 kilometer meter, but this is downward force will create the negative bending moment. Accordingly, the bending moment diagram can be drawn. So direct joining of 2 points will give you the bending moment diagram. So you place from this point to this point. So whatever the values you are having from the neutral bending moment line, your positive values will be marked on the upper side, and the down bottom side you can mark the negative side. So that's all about the bending moment diagram for the given overhanging beam. We will move on to the next topic in the next class. Thank you all.